So I'll tell you this. When did you use this formula here?
The last problem.
The last problem. Because the last problem wants a grade, and you want to convert a z back to a grade. That last problem, of course, drove me the craziest because it drove you the craziest. But, so, what does this notation mean? Percentile. So like the xth percentile, right? Or the eighth. This is the what percentile? No. 50th percentile. Why? Why is that the 50th? Because it has 50% below it. What does a percentile always mean? That percentage is below. So if I want the top, let's just say top 11%, because everybody had that, but nobody had that. Top 11%. Where's the top? These are grades, right? So where's good? Top 11% should be good grades. Where are they? Over here. Top 11%. So if you had 9, it'd be in the same place, 0.09. All right, so I give you a percentage. What do you need to look up to work your way back to a grade?
The area.
That's the area, but you look it up to find the what? Z-score. Because then you can transfer that back into a grade. So I want to know, how far up do I have to go to get to where the top 11% starts? You guys with me? So this person right here is in the top 11%. It would be 6% or 9%, whatever the hell numbers you guys have. So if I find how many steps to go up from the mean to get there, I just do that. I take that many steps above the mean to get there. That's why that transforms it back into a grade. So I know that grade should be higher than the mean because I'm in the top 11%. I should be higher than average. So a lot of you guys are putting them down here. That's no good. That's the bottom whatever percent. I want the top whatever percent. So that was the one problem. Yes, the one problem where you had to use this equation, that backwards transformation, because you get the z-score and you want to know what the x is. In this case, the grade. Okay. All right. Anything else while it's in your brain? Anything else freaky from there? The rest of it should have been roughly nuts and bolts.
Actually, do it because
So, yeah, I don't think anybody had this. So if you look up 0.11, what's the closest I can get? And what kind of z-score is that going to be? Positive. Now, if I look up 0.11, am I going to get the right number? No, because the chart only understands area that is below. So what would this area be? 0.89. 0.89. The chart only knows areas that are below a z-score. So if I want the z-score that's got 11% above, that's the same as the one that's got 89% below, and that's the number the chart understands. So if I look up 0.89, what's the closest I can get to it? Looks like 0.8907. And what z-score is that? See, 1.23. So your z-score should have been like 1.3 something, somewhere around there for most of you guys. Some guys said 9, 6%, 4%. Maybe. And now, how do I change that back into a grade? I take the mean, what was it, 73.1? No, it was different for everybody, so whatever the hell the mean was. So I take the mean plus 1.23 times whatever the standard deviation was. And I wish to God everybody could see this, and I know I'm the weird-ass math teacher that loves math. I'm all weird, but all a z-score means the number of steps away from the mean to the data point. So if I know I am 1.23, how do I know I'm this? Because I want exactly 11% above it, and that's the z-score that does that. So I know I'm that many steps above the mean. Bam! That's why it's going to transform back into a grade. So much of this stuff makes physical sense if you let it. Okay, baby. All right, some of you guys are like, yes, please, dear God, keep going. Is that all right? I mean, all right. So I really wanted to do that because I needed to give you a chance to do some of this without a safety net. because now we're going to get back into what we started to get into last time, which is our first tweak to this. What's really interesting, sure, I'll use that word, is that it takes me a long time to explain the concept, not because I'm slow, but because the concept is weird. But the actual change to your work is minimal. It's crazy. It's really kind of awesome. So remember, if you were here last time, remember we were talking about alternate universe Florida, or Florida with the ages and stuff. Remember that? You guys are like, I don't remember what I have for breakfast, Jeff. All right. So what happens if you go back to that clip and you look at it? We had something that looked like this. Wow. Ages in Florida. Remember that? And this was created by plotting individual ages. How old are you? I'm this old. Bam. How old are you? I'm this old. Bam. And then just plot them. So nobody happened to be in here. Does this look normal? Hell no. So what's really neat, to cut to the chase, I'm not going to redo what I did last time, because it's on video. It's up on the YouTube, it's on the internet. If I have a sample greater than 30, what results, which means if I get a group of more than 30 people, how likely is it that I get only people that are here? Is that very likely? If I take 30 randomly selected people in Florida and I get nothing but 3 and 4-year-olds, is that normal? Is that expected? Should that happen a lot? No. Could it happen? Yes. Will it happen a lot? No. So again, remind me, what's the most likely thing to happen? You guys remember?
Ages in the middle.
There's nobody in the middle. I think you're saying the average would end up being in the middle, because what's the most likely sample I would take? A mixture of people here and there. Does that just make sense? If I take 30 randomly selected people, I'm not going to get only 90-year-olds. I'm not going to get only 10-year-olds. I should normally get a mixture of older and younger people. And if I don't, if I get them, every one I pick is 3 years old, but I pick them at random, I'm like, what the shit just happened? It's like flipping a coin 20 times or 30 times and getting nothing but heads. That's not impossible, but holy shit. Okay, so I like it. So again, like, yeah. So what's neat is, I don't care what the distribution starts off as, it could be whatever the shit. Once I get above 30, and I plot the means, I take 30 people, or in this case, let's say 31 people, and I take your average and I put them there. I put a dot. So what's the difference here? This dot would be what? That dot right there would be a person. A dot I put here would be an average of a group. In this case, I think I said 31. That's the fundamental difference between these pictures. This is the individuals. This is all groups of size, whatever, in this case 31. It ends up looking like this. With the same mean, I'm trying to get in the same place, but I didn't quite. Oh well, too bad for me. Same mean, which only makes sense. There's an average age in here right now, correct? How would I figure it out? I would take each person's age and then average them. What if I take 2 people at a time? Get their average, get their average, get their average, and then average all of those. Will the result be different? Really think about it. If I take 2 people at a time, have I changed who you are? If I start taking 2 people at a time, do some of you guys suddenly get older? Wait a minute, stop, Jeff. You're the same people. I don't care if I take you 1 at a time or 2 at a time, I'm going to get the same average. Does that make sense? Okay, it has to. Please let it make sense. So if I take 30 or whatever number of people at a time, and I average all the averages, it's going to be the same as the average was before. What changes, though? A couple things. It definitely looks more what? Normal. Shit, when it's above 30, it's going to be approximately normal. Enough. When I say enough, what do I mean? What do I mean? What do you mean, Jeff? You're like, I don't know what you mean. You're the one saying this shit. What is it that I hope I could use? This guy. Because what is this guy? Z-score chart. But what's he got? Which are all of the answers. So holy shit, I got a sheet of answers that I can only use if I know my curve is normally distributed. So when I say normal enough, I mean enough to use that chart. So could I use the chart for a problem from this? Hell no, because it's not normal. But if the question said you took a sample of more than 30, what's the probability the average mean is somewhere? I can use the chart. So this is something called central limit theorem. And one thing it says is the mean stay the same. Oh shit. What does this mean? Tell me again. What is this a picture of? Any dot I pick is a what? An average of a sample, right? So every dot I pick would be an X bar. So really, this thing in the middle is the mean of all the means. This guy has got a little subscript. This would be the mean of all the X's, the individuals. Which one has a smaller standard deviation? The top one or the bottom one has a smaller standard deviation. Bottom one, because what's standard deviation tell you? The average distance from the mean. This one, there's a ton of shit right next to the mean. So this has got a much smaller standard deviation than that one does. So, central limit theorem says the mean stays the same. The standard deviation becomes, now here's the neat thing. This little piece right here is interesting. The standard deviation gets smaller by exactly this much. Yes?
You don't want to turn the camera because
Oh, thank you. I always appreciate any camera help. This one is a little bit freaky because the actual math behind why is it exactly this is a little bit hard. But I always thought it's better to see this as a variance. How do I get the variance of this picture? I divide this guy's variance by n. As my sample gets bigger, I should expect more and more of them to be closer to the average. So again, if I go out and take one person at random, am I freaked out if they're taller than 6 foot tall? Not a lot. I'm not very freaked out. Take two people and their average is more than 6 foot tall, I'm a little more freaked out, but still. If I take 38 people and their average height is more than 6 foot tall, okay, that's weird. Because it should be where? To take 38 people, their average should be close to the real average, which is like 5'9". And they have an average greater than 6 foot? Holy shit, why is it so weird? Because I expect them to be closer to the mean. So as my sample gets bigger, my standard deviation gets smaller because they all sort of come closer to the mean. Okay, maybe. So to be honest, that is the only real change in the work we do. Is I can't use this guy, I've got to change it. All right, before we do an example problem, the third thing is for n greater than 30, the result is approximately normal. So let's take a look at this picture here. This might make a little more sense now that I talked a little bit about the idea. Everybody's got this dude, right? Yes.
I'm confused.
Yes.
So for the second one, the under the central limit theorem, why would they use?
That's the one I said. That's a little bit tougher to show mathematically, but I want it to make sense just in general as my sample gets bigger. I really want this to make sense. For individuals, can individuals be wherever the shit they want to be? Yeah, most of them should be close to the mean, but it wouldn't be weird if I found somebody who was 5 foot tall, 6'5". Wouldn't be like really weird, right? As I take a bigger and bigger sample, if I take 5 people at random and their average height is 5 foot tall, that's starting to be a little weird. Does that feel right? Because what should happen to groups of 5 people? Their average should be closer to the mean. Now what if I take a group of 50 people and their average height is 5 foot tall? Then I'm like, holy shit, because for 50 people, I expect them to be even closer to the real mean. The larger the sample I take, what should happen to the sample mean?
It should get smaller.
It should get closer to the real mean. So there's a real average age of Grossmont. If I take 30 students at random, their average age could be kind of different. If I take 800 students, if their average age is really different, then something's probably wrong with what I thought the average age actually was. Do you guys see that? So if somebody thought the average age was 27, and I take 800 students at random and it comes out to be 22, that is evidence that they're wrong. That's going to be chapter 9. It's when we test claims. Somebody makes a claim and we test it. And we say, you're full of bullshit if we get us too far away. Yes?
So why would it be squared then? Like, where is the back?
Oh, I was just saying, there's the official formula for standard deviation. If I square everything, it becomes, oh, I'm sorry, that shouldn't be a square root. Is that what your question is?
Okay.
That's my bad, my bad.
No, you're good.
So I said it and then I wrote it different. You divide the variance by n. So you get, yeah. And then when I square root everything,
Yeah.
all right, thank you. I like it. So I can't fully explain, with the amount of math that most of us know, why this formula is true. But I want it to make sense as far as I should get smaller as my sample size gets bigger. If I take larger samples, they should be closer to the mean. And what does that mean is happening? The standard deviation is getting smaller. If I take the entire population, they all go right, then it becomes this, the standard deviation becomes 0. Holy shit. Yes?
No, I just know what you said made sense.
Oh, thank God. All right. This is always my hope. And some people I hear are like, that's good for you. He still hasn't made sense yet. Shit. There you go. All right. So, let me ask this again. Does anybody still need this guy? Oh. So we did the other side in class before. So we haven't talked about this side, I don't think. Oh. All right, I don't want to spend a ton of time with this, but holy shit. You guys all right? Anyway, disappeared? No? Huh? You need this?
Yes.
What do you need? You need a pen? Neato. Do you work? Sort of. All right, guys, real quick. This is this is my attempt at giving you a concrete example of what the shit I'm talking about. This is not concrete. I made up this Florida. Yeah, whatever, Jeff. You can say whatever bullshit you want to. You're making it up. This is concrete. Numbers in a hat. Every number has a 1/4 chance of happening because there's 4 numbers in there. Are you guys with me so far? So, of course, if I graph it, it's going to look like that. It's going to be uniform. They all have the same probability. Okay, maybe. And then I've got this little dude that I can create. And then I can calculate these. The mean and the standard deviation, you could double check me if you want to. Right? You can make x p of x, x squared p of x, which I'm sure you all are going to do. And then you can double check what I get. Is everybody with me? Yes? No? Maybe so? No? Okay. So again, how do I get the mean for xp of x? I just multiply each one of these and add them all up, and that's what you get. And why does it make sense? It's right in the middle because they're all equally likely. So it actually is going to be right in the middle. Standard deviation, x squared p of x, add them all up, throw them in the formula. I'm telling you, you're going to get that. And if you don't, trust me, you can do it yourself. All right. So that's what the last quiz was on, really, the one before today, was the xp of x stuff. Okay. Is this ugly? No. It's nice. But is it normal? No, it's not. It doesn't start low, go high. Now, when I said we would take groups of whatever and plot their average, I want to give you a concrete example of that. I had to make this kind of a small this is my population here. I had to make it a small population so that I could fit it on one sheet of paper. So for example, if I reach in and take one and then take another one, I could get 1, 1. Or I could get 1, 2, and so forth. So I listed all the samples I could get. These are like the samples of people. Possibly, right? In this case, it's just these numbers. And then in yellow are the sample means. So why does it make sense the most common sample mean is 2.5? Because that's the actual average of the numbers. Okay, maybe. And it's very hard to get a sample mean of 1. There's only one way to do it, and there's only one way to get a sample mean of 4. But there's several ways to get a sample mean of 2.5. So if I look at the new graph, how many 2.5s are there? 4 out of 16. So that's going to be the tallest peak. Does it look more normal now? Yes. In fact, if I redid this whole problem and you guys picked 4 numbers, it would come out very similar to this. It would start off uniform, and then it would become more normal. Okay. And if I redo all the work for this to find its standard deviation and so forth, I get the same mean. The mean of the means is 2.5, but I get this standard deviation, which is equal to the original standard deviation divided by the square root of 2. What's 2? Why is 2 there? Yeah, my sample size was 2. If I would have picked samples of size 3 and listed them all, there would have been a lot more of them, right? But this would have come out to be a number that was that divided by square root of 3. It would get even a little bit smaller and then a little bit smaller. Okay, so again, if you want to, you can double check me, make sure the numbers actually come out. But here, let's do a concrete example of what the hell this thing looks like. So for example, we know, let's see if this pen's better. All right, we know that the mean of something is 11, and the standard deviation is 2.9. We take a sample of, let's say, 42 things. I love how specific I'm being. Is everybody with me so far? So we know that the mean is 11 for some collection of things. And the standard deviation is 2.9. So it could be kids' ages. Kids in a room, average age is 11. Standard deviation is 2.9. You guys with me? So if I took 42 kids out of this room, and I take every possible sample of 42, what's the probability that the sample mean is going to be less than 12? All right, let's see how this works. So do you see there's a difference between this problem and problems we've done before? Every problem we've done before now has been pick one thing. Pick one person. What's the probability their test is this? Pick one whatever. Now we're picking a sample of stuff. So how do I know when to do this? When I take a sample and I ask about the sample mean. So did I take a sample of things? Yes. Am I asking about the sample mean? Yes, I am. This standard deviation, what does it tell me? It tells me the spread of what? The spread of individuals. And my problem is asking about a group of 42 people. I can't use the spread for individual ages for a group of 42. I need to know the spread of all groups of 42. I need to change the standard deviation. This one is for individuals. I need the one that is for groups of 42. And again, I could have just said this and just skipped all the conceptual discussion, but I hate doing that shit. But what is a trigger now? I took a sample and I asked about the sample mean. I know I have to change the standard deviation now. I can't use this guy. because he only works for questions about individuals. How do I get the one that works for this problem? I take the old one divided by square root of n. Yeah. So what's the old standard deviation? The one for individuals, 2.9, divided by what? Square root of? What's n? 42. Right? Took a sample of 42. That's n. Thank God. N always means the same thing. Thank the gods. Somebody help me out. What do you get there? That's true. And 0.447. I love it. So this problem is talking about a group of 42. I cannot use the spread that works for individuals. I need the spread that works for groups of 42. That's what that step is. So how do I know when to do that step? When I take a sample and I ask about the sample mean. And now every step after this is the same. So this is why it's so freaking important that you get the idea of just a normal z-score problem. What goes in the middle? Oh, by the way, why can I even draw this picture like this? How do I know it's this? N is bigger than 30. My sample is bigger than 30, so I know the means will become normally distributed. Thank the gods. If I would have put 22 here, we would have been completely screwed. Actually, in a sense, it'd be an easy problem. You just say, can't do it. Please understand, I'm never going to give you a problem like that. That would be so mean. Some of you guys have more time for the other ones, and some of you guys are doing this whole problem and you shouldn't. That would be so evil. I'm not quite that evil yet. But if I did say 22, we officially could not do anything. Because I don't know what it's distributed. I don't know what it looks like. Since this is greater than 30, I know it's normal. What goes in the middle? 11. And where's 12? So I want, this area here. Going to make this into a z-score. So every step is the same now. It's just what standard deviation am I going to use? This one. So when I go to make the z-score, it'll be my data point minus the mean divided by the new standard deviation. So this is what I meant. It took me the longest flipping time. I made a handout that is the most colors ever. 2. Watch out, Jeff. Right? Just to explain the idea, but it ends up doing the most tiniest tweak to the problem. Just change the standard deviation. So what do you get for that z-score there? 2.24. Then I look it up in the chart, and I'm going to get the answer because I want the area below. So the only difference between this kind of problem and the problems we've been doing is I have to change the spread number because it's not individuals, it's groups now. So when you look up 2.24, you're done. What do you guys get? I get 9875. Okay. Let me give you this. We're just about out of time. Here's the practice test. Yeah, please don't forget your IDs and stuff.
percentile.